Hi, welcome to part 4 of the Padauk 3-cent microcontroller programming series, where we build up open source hardware and software to program these 3-cent microcontrollers. Now, in part 3, we looked at, we got our programmer up and running. We installed the firmware on there using DFU mode. So in theory, the programmer is ready to go, but we haven't tested it yet. So this video is actually going to be about using the SDCC, or the small device C compiler. And this is a compiler that supports the Padauk microcontrollers. A lot of people on the EEVblog forum actually worked very hard to get all this stuff working. So we now have a proper ANSI C compiler that supports the Padauk. So yeah, can we actually use this SDCC to actually compile a program for one of these Padauk microcontrollers, so that then we can generate an Intel hex file to then use in the next part to actually use the programmer hardware to program it? Sounds easy, but as usual, you know, there's lots of hoops to jump through. Right, so how do we program these Padauk microcontrollers? Well, of course, you've seen in my previous video on this, we can use Padauk's software, which is C-like. Kind of, it's not really C, it's Padauk's C. And the whole point of this is now that you can use an open source, like proper ANSI C compiler to do this. And to do this, someone, I don't know who, sorry if I can find the name, I'll put it up, SDCC small device C compiler. And this is an open source C compiler, and it's regularly updated. As you can see, it's, you know, just updated in January 2020 4.0 release, and it supports all these architectures, 8051, which is now used in, you know, a ton of generic microcontrollers from Asia, because they're using little farty novelty gadgets and greeting cards and things like that, because you don't pay any royalties on the 8051 architecture anymore. So yeah, it's got Rabbit 2000. I used to do Rabbit 2000 back in the day. I used to love the Rabbit 2000. It had like 4 serial ports on it. That was, whoa, fantastic back in the day. And it also had a great deterministic real-time operating system as well. That was like really easy to use. EZ8, anyone use the old, anyone use the Zolog Z80 micros anymore? STM8 and Padauk and PIC micros available as well. And yeah, so it supports, I'm not sure if it supports all of the Padauk microcontrollers, but you know, it's going to support a good number of them, so in different various packages. Now, this is a command line compiler. As far as I'm aware, there's no IDE or integrated development environment for it. So yeah, use your favorite Notepad++ or whatever it is you want to use to write your actual programs in, and then you can just call the compiler. And there's probably, like, you know, various scripts and things you can do to automate all sorts of processes. But the general thing is, you write your text file containing your C program, you run it through the SDCC compiler, you know, with a specific target to whatever Padauk microcontroller you're using, what part number you're actually using, and then it will generate a binary file, which then we can use our newfangled programmer to program into it. So unfortunately, it's not like a seamless automated system like you'd get with your PIC or your AVRs, and it's all under one environment and all just seamlessly works. And like, you know, you push a few menu buttons at the top and it compiles and downloads and does everything for you. This is a bit, you know, it's a bit more tedious, but these could get better over time in terms of like integration support, scripting support, and things like that. But in this video series, the aim is just to write a standard ANSI C program, compile it using an open source compiler, and then program it using our open source hardware. So you don't have to, all you have to do is buy the microcontrollers from Padauk. You don't have to buy their secret squirrel hardware. You don't have to use their secret squirrel C compiler, integrated environment and things like that. It can all be done using open source tools. Cool. Now, which Padauk microcontrollers does this support? Well, it's new in development, a backend for the PDK-13, which is a 13-bit, which is the developers' names for the 13-bit wide program memory architecture. And like previous releases down here, they've actually added support for the PDK-14, as they call it, the 14-bit wide memory, and the 15-bit wide memory architectures as well. Now, if we go over to the GitHubs for the free PDK, as you can see, they've got the programmer software, they've got code examples, they've got looks like evaluation boards, Then they've got documentation for the programming architecture. Then they've got the program hardware, which we've just built. And they've got an emulator as well, VHDL emulator to emulate the core. That seems pretty cool. So yeah, you don't even need to buy the micros from Padauk. You can put it in an FPGA. I don't know. Does anyone want to try that out? Give it a bell. They've got disassemblers as well, and they got code examples and stuff. Like, wow. Hats off to everyone who's contributed to all this, because it went from, you know, this weird, obscure Asian brand micro with, you had to buy the programmer, you had to use their quasi-C like compiler, and that was it, to now it's like they've practically completely opened the whole thing. Amazing. All right, so if we go into code examples over here, here we go. This is from like 2 years ago. It's been around for quite some time, but let's try and just blink a LED, shall we? Simple blinking program. So let's go to the simple blink subdirectory here. We've got our C program. That's it. We don't want our project or we'll just could. But anyway, we've just got our C program. Here it is. Simple blink program. That's all it does. And look, it's incredibly simple. Then you've got port AC. I don't know what the labeling is. Anyway, it's that port and that pin. So it doesn't matter whether you're using an 8-pin Padauk micro or using like a 14-pin one or whatever size chip you're using. It'll have all the different ports on there, and you can choose whatever pins you want. So that's actually bit 3 on there, and then you can use the pin out diagram of the chip to actually translate. We've got that over here somewhere. Yep, that's over here. There you go. PA3, there you go, is actually this pin down here. And I believe the 8-pin chip will just use the bottom 8 pins down there. So it's the same pin out. So it's got VCC and ground like that. And on the 14-pin chip, they're in the middle. But on the 8-pin chip, the pin out should be exactly the same. So PA3 will be this pin down in the bottom right corner down here. And that's the pin that we're going to actually toggle. So we'll just download SDCC here. Let's go to the download page. Win64, that's the one we want. Version 4, because that supports the latest one. You always want the latest. Don't always want the latest version. Might be some obscure reason you might want to use an older version. But anyway, let's just run that. And, set up. Nice. 300 other people have downloaded it. Yep, we want to include, there we go. Let's include support for everything, shall we? There we go. We can get PDK 13, 14, 15, and I don't know what the Stack Auto library is. No idea. But we want to install. Should we, you could just disable everything else, but it doesn't matter. I'm just going to go, yep, install, no wuckers. And there's all the pick files, there's all the header files. We'll see the PDK header files shortly. Blink and you miss it, blink and you miss it. Whoa, missed it. Oh, hang on. I looked at the simple PDK code examples. Is that different to the SDCC PDK code examples? Yep, I think this is the one we want. Kamagutsa, count PFC 151154. Don't know what chip I'm going to be using yet. Let's do hello. A timer LED example. So it's going to flash LED, is it? For the, I don't know. It looks like they've got like a demo board thing. So I don't have a demo board. I'm just programming the chip. So here's these eval boards. Let's go to the SO8. Oh, it's just got schematic. No, what's... no. .sch. No, let's not go there. Anyway, count.c. Let's have a look. What's in there? A 4-bit counter for the Padauk 151, 154, 161, blah, 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 blah. Counts seconds from 0 to 3 in binary using 2 LEDs on the lowest and highest ports of port A. Written by Philip Klaus. There's no way I'm going to pronounce that correctly, I'm sure. Anyway, standard bool.h. Okay, this is more your familiar C stuff. So all your C aficionados are going crazy. Now, I'm actually starting to think that this simple PDK code example that we looked at, that is actually only going to work within the Padauk environment. So we don't really want that. We want ones that work for SDCC. Yeah, so it looks like we should be using this SDCC PDK example, which unfortunately is a bit more complicated to set stuff up. Now, if we go into the bin directory of what our SDCC compiler has installed, we'll find that like there's S51, for example. So that'll be the 51. Yep. Helps if I type it right. SDASPDK15. Boop. And there you go. That looks like our assembler. That's the assembler written by Alan Baldwin. Good on you. Awesome effort. Absolutely no warranty implied. But yeah, so this is what the compiler will call. It'll call up this assembler, which actually does the actual hardcore work. It'll actually call up this assembler when we tell it to target the Padauk microcontrollers. It'll know to call this up. So unless you wanted to write Padauk assembly language, for example, because the whole idea of the C compiler is that the C compiler then converts it into assembly language, and then the assembler actually compiles it into the binary. So yeah, it's just calling this up. So unless you want to write assembler, you wouldn't muck around with this. But we can run our SDCC, and whoa, there it is there. It's lots of options. Lots of special options. We probably shouldn't have installed all of the micros. We should have just installed the Padauk ones. So there's the Z80. You know, there's all the different standards it supports for those playing along at home. If we go into our free PDK section here, we can find the instruction set. There you go. So let's go for the 15-bit instruction set. And, oh, it's just a HTML file that will give us the instruction set. So we can download that. So there you go. If we call that up, there's our 15-bit instruction set. Cool. Wow. Somebody's gone. Hats off. That's a lot of effort to reconstruct that and get it right. I'm sure there were bugs in the early version, but you know, as people use it, it gets ironed out and it becomes rock solid. Sweet. Unless they make changes to the hardware. So I thought I'd just have a googly search for integrated development environments for SDCC. It looks like there's one, this SourceForge, one IDE integration, Eclipse perhaps. There's this Xanadu one down here. I don't know. Some hardware vendors have created IDE bundles supports for their hardware. The Pinguino IDE bundle, which is the PIC version. What about this Xanadu? An IDE for SDCC, Xanadu for small device C compiler. Sounds alright. Unfortunately, this looks very old. Like, latest commit was 2017, but look, you know, and I don't even think there's, I don't think it's a Windows one. So, system requirements, Python, nah. So I thought what I'd do is just, I'll use Notepad++ here. I cut and pasted this code for this. I don't expect it to work because I suspect it only works with the Padauk programmer, you know, environment quasi-C compiler, but it's worth a shot. Basically, you're just learning as I learn here. I'm just like going through until I get something that works. But the good thing about this is that this is how you can expect to, you know, if you're in the same position I am, oh, I want to use these Padauk microcontrollers for something, you know, I've got a specific application, I've got to build up the hardware, we've got to, you know, download all the stuff and figure out how all this works. And of course, I just ran a simple with no parameters whatsoever, and it simply did not like test.c. It just wouldn't pass it at all because we've got the dot delay there. So yeah, it doesn't like that. That's a Padauk thing. By the way, I looked in this timer IRQ example, which is an interrupt example, and it seems to mix. Like here's some original code that they copied, original mini-C code, and then they, looks like they're mixing, like this is how you mix ASM. You just go ASM eng-int, don't know what that is. Maybe hello C. I like the idea of hello C. Does it simulate a serial port or something? It outputs the string hello world at 9600 baud, one stop bit. That's what we want. Good on ya, Philip. With 2 P's. Wow. So here's all the code. So this is like, you know, it's once again, they're mixing ASM. They've got engint. I don't know what that is here. So it's not the world's simplest stuff. Like I'm not the world's best programmer, like SFR at address, you know, use factory calibration code and all this sort of stuff. So it's not the It's not the easiest thing to use if you're a newbie, that's for sure. But anyway, it's going to use printf. It's going to put, it's going to call the code. It's going to assemble the code, include the code for printf. I don't know how much memory that will take, because printf is usually, quite a memory hog. Many times I've had to avoid using printf on small micros because of, it can take a couple of kilobytes of program memory just for printf, for example. So yeah, you can really come a gutser on that. So anyway, we seem to be able to use printf here, but it's probably optimized. A good optimizing compiler will take out stuff you don't need and things like that. So anyway, I like the idea of having a hello world example running on that outputs a serial port. I think that's a very worthy example. So I'm going to copy that and we'll just paste that in here. There we go. And we'll save that as our test.c. And I like that it's got color syntax highlight. And I can remember when that was introduced, that was a big thing. Color syntax highlight in your code. Whoa. So here we go. Let's try this again. Once again, I've got no target whatsoever. I haven't used SDCC before, but it seems to simply go in and at least first pass the code. Absolute address for SFR, probably out of range. Probably. We don't care about probablys. We deal in absolutes. Only a Sith deals in absolutes. Anyway, probably out of range. We don't care about that. Cast of literal value to generic pointer. I don't know. They're only warnings. They're not errors. From type const unsigned in literal. Error for fopen failed on file test ASM. Yes, because we haven't specified, I presume that's because we haven't specified an assembly target, i.e. a particular Padauk or some other microcontroller, Z80, 8051, whatever it is. It's just compiled that C program for us. So that's what it does. It compiles the C program and then it converts the C program into assembly language because we haven't told it a target. It goes, I don't know, what architecture do you want me to assemble this thing for? I could just, go for an example somewhere, or maybe someone's got a command line example, but help execute. Actually, I like to execute verbosely. Compile and assemble, but do not link. Preprocessor. Do we have to do -m and then put PDK or something? Because it's used the EG example of the Z80. And then you've got to select the specific processor. Oh, yeah, I can muck around with this for a while. I'll see if I can find a command line example just to do it, just to get us started. That's the best way. I mean, you can learn to do it by failing here. That's fine, but yeah. When in doubt, RTFM. So we can go down. Wow, they've really gone to town on this. It looks like, though, they have a wiki. So let's go over to the wiki. Wiki's gonski. Oh, well, maybe somebody didn't update that. Anyway, let's see if we can find some command line options. So what I did is just search for the word Padauk, and there you go. -MPDK13 for the I better figure out which one I'm doing it for, but let me just try the 15-bit wide one, shall we? So can we just do that and try it? Nope, didn't like that. Test ASM. So, silly me, that's not for the SDCC. That's the... Is that the linker or something? Yeah. Dumbass Dave. It's got specific entries on Padauk intrinsic namespaces and stuff like that. Very nice. Looks like the Padauk is somehow tied to the 8051 type. Oh, that's it. That's it. Where do we have processor target support? Processor selection options. There you go. That's what we want. Processor command line option. No, that's SDAR. That's SDAR to manage libraries. No? Okay, we're back to where we were. All right, looks like it's going to be more complicated than I thought. And of course, where else are you going to find this but the EEVblog forum, which is, I think, pretty much where it all started with the original reverse engineering video from David 2. He was experimenting with, just looking at the signals from the Padauk. And I think it all sort of started to flow from there. Anyway, this is a message from JS, blah, 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 lots of numbers. And down here, we've got an example. Commands to compile. Here it is. I was right. SDCC MPDK14. Oh, I didn't put the -C, but I didn't have the extra stuff. But I was close. I was close. So anyway, we should just be able to put that, I guess. So if we do the example they got there, SDCC MPDK15-C test ASM, it doesn't work. And if you add in the -O and test.rel or whatever, it just gives you the same thing. And by the way, that line 105 there where it's getting the error, the program's only 104 lines long. So the 105th line is just basically saying that it can't open the file test ASM, which is what it would have generated if it knew what processor target it was compiling for. Because you can't compile to an assembly file unless you know your processor target. And I think SDCC just assumes it's 8051 target if you don't put anything. Oh, I figured it out. It was simple. I was actually running the program. I had my source file in the Windows program files subdirectory, and I was calling it up from there. And that's actually a Windows protected subdirectory, so it wasn't actually able to write. It was Windows actually stopping it from being able to write to that same subdirectory. So I just created a subdirectory called, /A on my C drive, and that's where I put my files. And here we go. Duh. There we go. I just had test.c in there before. Now I've got test.asm, test.list, test.rel, test.sim. Oh, unbelievable. Dumbass Dave. So what we have to do here is this multi-step process is produce this rel file, and then we've got to do it again. So then we just have to go test.rel like that, and then the output, got to take out the -c there, and then test.rel, and then the output file test.ihx, which is the Intel hex format file, and that should work. And we should now have, ta-da, there you go, 936 bytes in all its glory for a Hello World program. That's pretty good when it's going to include like a printf thing. That's great. There's the Intel hex file. We can actually load that into here, and it should actually display the hex file. There's our Intel hex file. So that is what we can use to now program into use our programmer software, our programmer firmware embedded here, put our chip in, and then with the right command line options in this, then you do it. Of course, yes, you could script and automate all this, and maybe there's already somebody out there who's done all this so that, or if you had, as I said, an IDE, an integrated development environment, specifically for, that supported Padauk micros and supported this particular open source hardware and supported the SDCC and all that sort of jazz, yeah, you could potentially just push a single button, compile and download program, and like in one hit, literally one button press, it could compile and then program in one hit. But it uses all these different command line tools to do that. But yeah, that's the value of scripting. So there you go. That wasn't too hard at all. But yeah, you got to know what you're doing. It's not trivial stuff, but even dumbass Dave was able to figure it out. But as it turns out, I've actually got a PMS131 chip in here, which in an 8-pin SO package, which curiously not even the datasheet has a pin out for. It's got like the 14-pin packages, it's got the 10-pin MSOP and stuff like that. But anyway, so I assume that this is like the 13-bit word architecture. This one's got like a built-in 12-bit ADC and stuff like that. So I'm going to do MPDK13. Now this is not tested yet, not like fully tested yet. So anyway, I'm going to recompile that. So I'm going to compile that. There we go. And then I'm going to, what do we do? Remove the compile, put in the rel, and then we put in the ihex like that. Ta-da! And we should have our ihex file for, text. Text? I did text. Should be test. Oh. Anyway, text. Oh, that's appropriate. We did a printf. Text.ihex. Actually, I'm going to have to rerun that again for text.round. Confusing myself. Anyway, this is for compile for the 13-bit architecture, so... Right, so we need to go back to our free PDK, the programmer software. We're going to have to figure out how to run the command line for this now. So here's our install README, and then it's got usage in here. Easy PDK program option, and then you can read, write, erase, start, and stuff like that. So presumably if you've got an, I don't know, do they have copy protection? Anyway, yeah, you can read back an existing, so if you have a product that has a Padauk micro in it, you can read back the binary file from it. So there we go. We specify our target, and we can read and write. There we go. That's what we want. -N. What's -N do? IC name. There it is. Yep, IC name. So presumably, cross my fingers, it supports my 131 chip. But now the thing is, where is the executable? Where is the Windows executable? Got our programmer source, but I want a Windows executable. Make file. I hope I don't have to build it. No, hang on. I keep going, and sure enough, browser open GitHub for easy releases. Oh, did I not see that? Okay, I must not have seen the releases. Awesome. Somebody's compiled it and released it. Fantastic. Okay, I now have that unzipped. Easy PDK prog. And what do we need? Well, we can list first. There we go. Oh, it supports the 131, PMS 131. That's the one I've got. Beauty. So /n PMS 131. Right. Oh, this is exciting. Text.ihex. Will it work? It's got some LEDs on it. I don't know. I don't know if the programming voltage hardware on here. We still haven't tested that. So I'm just going for broke here. Let's give it a whirl. Right for this IC. Oh, bloody Murphy. It's okay. I found my tubes of PMS 151s. Hopefully that works. They're 8-pin SO as well. All right, let's do this again. So I've got to recompile for I assume it's the 1.5. I assume the 151 is the 15-bit architecture. Probably a poor assumption on my part, but anyway, so I'll do that. And then so I'm doing test this time, rel, and then IHX, no definition of area home data. Ooh, link warning, internal version error. Oh, that's interesting. Did I forget to put the -C in there? I think I might have. I think that might make a difference. Let's try it again. Okay. Then we take out the C. And we do the rel, and we go to the ihex. Ta-da! Winner, winner, chicken dinner. So we have test.ihex there. Yep, there it is. 4:37. Yep, and that's right about now. Oh, you can see the date and time that I'm making this video. Yep, we're good to go because it's a 4-part video. You might not see this for like a week or two. Who knows? So let's list again. PMS 154. Oh, C or B? I've got C. PMS 154C. I'm pretty sure that matters. So 154C, write test.ihex, fingers crossed. Will it go flishy flash and will it write it? Error. Command ACK. Failed. Wrong ICID. Oh, ICID. Wrong ICID. What? So it tried to read the ID from the chip and it didn't, I guess? Is there a bad contact in I got the SO8 adapter plugged in. I've got the chip around the right way. But But yeah, these are all these little things are what you have to go through when you're using something like this for the first time, or even coming back to it. Like I could do this now, come back in 3 or 6 month time and forget how to do all this. I'd have to watch my own tutorial or go to someone else who's, it's just nuts. So no, or there could still be something wrong with the hardware. We could, because I don't know about the programming voltages. Maybe it needs that to read out needs that to be working to read out the ID. Let's try it again, just in case. No. Okay. Definitely put in a 154C. Aha. People are probably screaming at me. Dave, look down this column here. The PMS 154C is a 14-bit in brackets. So there you go. I've Kamagata. I assumed, you remember how I said before, I assumed that the 15X series would be the 15-bit. It's 14 bits. And the 154 up here, which has the flash, they're all 14 bits. So I need to recompile again with the, here it is, with the 14, right? That's probably why. I can only assume that's why. Here we go. So compile that again. And then do that, change it to 1.4, test rel, test Intel hex. Okay, and now we can go to write that. So let's try it again. By the way, there's one thing I noticed. All these chips have the numbers rubbed off them. There's nothing, well, not rubbed off, there's just no numbers on them. They're blank. Great if you want to copy protect your product, I guess. Well, it makes it harder, Anyway, here we go. Tongue at a right angle. Aha, we can use the probe command. There you go. Thank you very much, JS, all sorts of 1 through 855 AA. I don't know what that means, but this is awesome. This is what makes the EEVblog forum great. It's basically the community members on here who've developed a lot of this stuff, and, I couldn't find this anywhere else except the EEVblog forums. Absolutely amazing. I probably wouldn't have figured out all this myself. So let's probe up the clacker. Probing IC, nothing found. So there you go. That's why. It can't read the ID. So there could be something wrong with my contacts, with my SO8 adapter. Could be something wrong with the chip, but that's, unlikely because I got them directly from LCSC. They're an authorized supplier, even though they got no numbers on them. Which is a bit of a worry. Or the hardware, there could be something wrong with the hardware. That'd be cool. I'd have to debug it. I just tried the 131. I probed that and nothing found. So, yeah, hardware maybe. Okay, I tried to measure the VCC pin on the chip when it, when I actually pressed program, and I had to put in min-max mode, capture mode to capture that. It only captured 0.55 volts, so yeah, I don't know if it's simply too fast for the multimeter to capture or whether or not there's something wrong with the hardware. Winner, winner, you know what? PMS 154B/C, I guess they're identical. There you go, IC ID. What it was is that, yep, dumbass Dave missed a joint. I missed it on the inspection, and yeah, I soldered that joint properly. It was on the DC to DC converter. So that's one of the things that I didn't do in the previous hardware testing. And yeah, Kamagata, see? If you don't test it, yep, Murphy will get you every time. Anyway, I thought I still had a problem because I tried it with the other chip, which I think is, because it's unmarked, the 131, and it didn't probe it at all. But then I put this one back in, and it's working. So I don't know if the 131 is just can't detect it or what's going on. So I don't know. So don't just assume that you've got a good chippity doodah in there. I'll try it again. I think that's making contact. No, nothing. Anyway, the 151's a winner. The 154, there it is. So let's go back and try and write this, shall we? Here we go. Oh, there's no LEDs. Oh, you may not be able to see that yet. Anyway, LEDs. Here we go. Done. It's only one-time programmable. I only get one shot at it, but done. The 154 without a letter on the end is a flash version, because if you do this dot list, it actually tells you the only flash part, or the only two flash parts. One is the 154. And the 154C is the and the B, which we've got here, which has got 2K words of memory, by the way. And as you saw before, we used 900 and something bytes. So we're using like half the memory just to do a hello world. These things are not designed for huge programs, but printf takes a lot of space. So, you know, you could, if you hard coded that in like, you know, handwritten C or something like that, it'd be much better. All right, so this writes hello world on pin 0 of port A there. So if we go have a look at our chippity doodah, 154, there we go, the 8-pin jobby, although they're all the same. It's all in Chinese, Mandarin, you know, whatever. Some people have complained that I call it Chinese and it's actually, you know, anyway. So there we go, pin 0, PA0, so pin 7 there. So if we hook up VDD and ground, are these 5 volt tolerant? I can't actually remember. So if we hook up 5 volts and ground, the good thing is that because I've got it in my socket, I can just take that off and stick that in my breadboard and we can play with this thing. Although, as luckily I've got a lot of chips because they're one-time programmable only. But you can buy lots of chips when they only cost like a couple of cents each. And yep, we can go to 5.5 volts. So there you go. That's handy. So we should be able to hook this up and we should get Hello World out and we should be able to view that on the scope. Let's give it a whirl. Will it work? After all this, how many videos? This is the 4th video. I haven't properly edited this yet, but this is probably the 4th video. It's like 2 hours worth of content or something. We're finally there, almost.